Okay, then I leave the floor to Dinesh Thakur, who is chair of session number 8. Please.
Welcome, everyone. Hopefully, you're well caffeinated for the next session, which is most of the speakers are virtual. We'll start first with the first talk from Ting-Chiang Fan on the topic crowd-driven mapping, localization, and planning. Just one tip for everyone, virtual presenters, if you have a lot of videos in your thing, just try to make sure you hit the optimize video tab in Zoom call. That makes it the video is not laggy. Ting Xiang, whenever you're ready.
Yeah, I'm ready. So can you hear me and can you see the slide?
Yeah, we can hear you. Your slide is not there on the main screen.
Okay. So can you see the slide?
Here we are.
Yeah.
Okay. So, hi everyone. I'm Ting-Xiang Fan from the University of Hong Kong. It is my pleasure to share our work, cloud-driven mapping, localization, and planning. In the beginning, I would like to introduce the background and the motivation of our works. When the robot navigates in human living environments, the dynamic pedestrians may hinder the robot's localization and planning. Therefore, traditional solutions often treat pedestrians as obstacles that should be avoided. In this work, we provide a new perspective. We use the observation of nearby pedestrians as another take of the sensory measurement. The cloud flow can encode not only the scene's traversable area, the red circle, but also human social navigation preference, the rectangle. So we consider the following navigation problem in the extreme case. Suppose that when the robot has no sensor mechanism for measuring geometry of static obstacle, and the robot can only perceive the movement of its nearby pedestrians, can the robot accomplish mapping, localization, and planning? To accomplish such a task, we propose 3 modules: Cloud Mapper, Cloud Localizer, Cloud Planner. So I will introduce the Cloud Mapper module. As we can see, a blue circle represents the local perception radius of the robot. Within the perception radius, the robot can observe the movement of the surrounding pedestrians. Then, we apply the clustering algorithm to model the movement into the cloud flow map. This map represents the pedestrian's move pattern in the environment. By fusing the local cloud flow maps, we can construct the global cloud flow map. The traversable area can be obtained after mapping. The mapping process is completed by the local perception of the robot. Here, we don't use any global perception system like bird view CCTV. By using the cloud flow map that we built, we introduce the particle filter-based approach with flow matching metric. In this video, we compare our cloud-driven localization approach with the pure odometry and the geometry matching based AMCL. The red dots represent the particle of our cloud localizer. As we can see, the pure odometry will drift at the beginning. For AMCL, the localization drift may occur at the intersection of clouds where pedestrians block most static landmarks. However, our approach may drift in areas with sparse pedestrians. But when the number of observed pedestrians increase, the drift can be corrected. This localization experiment shows that the cloud flow sensory is complementary to the geometry information for the localization. Note that our system is not a SLAM system. It cannot achieve the mapping and the localization simultaneously. Most SLAM's approach relied on the instant and time invariant features. For example, a point cloud features in LiDAR SLAM and image features in vision SLAM. These features are time invariant and can be observed instantly. However, the cloud flow feature cannot be observed instantly. In our cloud-driven system, as shown in the figures, the quality of the cloud flow feature will be improved as the time increased. For these areas where the observation time is short, their cloud flow features cannot be well obtained. So we cannot accomplish the SLAM system for now. Next, we propose a cloud flow map can help robots achieve the social aware planning. At the beginning, we first define the high quality social aware planning that can minimize the interdisturbance with the cloud. So we can use the number of the robot's active collision avoidance action to quantify whether the trajectory is socially compliant. As we can see, a traditional planning algorithm, A*, can generate the shortest trajectories, but the shortest trajectory would disturb the movement of the clouds. However, the trajectory generated by our social aware planner may be longer, but it can lead to less disturbance for the cloud flowing. For the traditional planning, the disturbance will occur in the entire trajectory. But the disturbance mainly appear in the intersection area for our social aware planner. We also deploy our system on a well robot to validate its feasibility and performance in the real world. To make a real scenario with dense pedestrians, we conducted experiments on a university campus at rush hour. We mount a 3D LiDAR and a multi-camera system on our robot to check the surrounding pedestrians. Conducting real-world experiments is not trivial. Beforehand, we need to calibrate the 4 cameras with a 3D LiDAR. With these sensors, we need to detect and check the surrounding pedestrians on limited onboard computational result. We first introduced the cloud-driven mapping experiment. We teleoperate the robot to construct the cloud flow map in this scenario. A point cloud map was previewed using LiDAR when the pedestrian's density was low. Here, the localization results are provided by the LiDAR and the GNSS.
Slow down.
Okay, we can perform mapping based on the movement of all pedestrians in this scenario. We highlight the possible cloud intersection in the cloud flow map in this scenario.
I think we have a problem.
I think, yeah, sorry, could you just give us a moment? We had a network issue here.
Because you were frozen at a certain point. Okay, now it seems to work.
Yeah, go ahead, please.
Sorry about that.
Okay. So frozen. I continue that.
I think the internet.
Yeah. Do I need to repeat this slide?
Yeah, just go one before. Just in case.
Okay.
Please.
Yes. So I will continue this slide or next slide.
Yeah, it's frozen again.
I think it's frozen again. I think the internet.
We can hear. Yeah. Oh gosh.
Can you hear me?
Yeah, we can hear you clearly.
So can you see my slide?
Just give us 1 second to set up quickly another.
Okay.
Sorry about this.
You're coming through fine to me on Zoom.
All right, go ahead now.
So I will continue my slide here or next slide.
This one,
please.
Okay. So we also deploy our system on a real robot to validate its feasibility and performance in the real world. To make a real scenario with dense pedestrians, we conduct experiments on a university campus at rush hour. We mount a 3D LiDAR and a multi-camera system on our robot to track the surrounding pedestrian. Conducting real-world experiments is not trivial. Beforehand, we need to calibrate the 4 cameras with the 3D LiDAR. With these sensors, we need to detect and track the surrounding pedestrians on a limited onboard computational resource. Here, I will first introduce the cloud-driven mapping experiment. We teleoperate the robot to construct the cloud flow map in this scenario. The point cloud map was pre-built using LiDAR when the pedestrian density was low. And the localization results are provided by the LiDAR and the GNSS. And we can perform mapping based on the movement of all pedestrians in this scenario. And we highlight the possible cloud intersection in the cloud flow map. Then we can use the cloud flow map for the cloud-driven localization and planning. As we can see, our approach can outperform the pure odometry method. Similar to our simulation result, our cloud-driven approach can achieve a rough localization in a cloudy scenario. For this campus scenario, with both pedestrians and vehicles, our cloud-driven planner and traditional planner can generate 2 different trajectories. And as we can see, the traditional planner will plan the shortest trajectory toward the goal. But the shortest trajectory will not consider the impressed social norms in this scenario. And as we can see, the robot will block other vehicles in this asphalt road. However, a social aware trajectory tends to cross the asphalt road first and then walks along the brick road. Actually, both types of roads are traversable for the robot. But our approach can interpret the deeper social rules in this scenario. In asphalt road, vehicles have higher priority, while in the brick road, pedestrians have higher priority. In this paper, we validate that our approach can only utilize the cloud flow information as the sensory measurement for robots mapping, localization, and planning. We show that the cloud flow information is complementary to the spatial information for navigation. In our future works, we can combine the cloud flow information and spatial information to realize the better navigation. Therefore, we propose the dynamic filter that can only remove the dynamic objects in highly cloudy scenarios. Here, we only present the simulation results. To watch the full version video, you can scan the QR code to visit our project website. And it is the end of our presentation. Thanks for listening.
Thank you. We have time for one quick question. Anyone? If not, I'll just ask one more of a technical question. Xinjian, that's a great presentation. Could you, in your simulation data, can you explain how you got the simulated human data? Or did you collect it with an overhead camera? And then also you had the mapping process. You had a multi-resolution map for the AMCL. How did you go about getting that?
Okay, so for the simulation, we use the MENG to simulate a highly clouded scenario or highly clouded pedestrians in our simulation. And for our real-world experiments, so you want to know how to check the surrounding pedestrians or how to mapping or something?
Yeah, so you had like a multi-resolution you didn't have for the occupancy-based mapping, right? So you're using your own way of keeping track of the pedestrian flow. So
yes.
So could you explain like how that data structure was stored?
Oh, we used the RGB camera to check the pedestrian's appearance, and then we project the pedestrian's bearing angle to our 3D LiDAR.
Okay. Right.
And then we can get a pedestrian's 3D position, and we can use some pedestrian's motion model to check the pedestrians in a surrounding environment.
All right, thank you. If no more questions, then we'll move on to our next speaker. Thank you, Xinjian, once again. So next we have Sheng Yan talking about visual semantic mapping and localization using parameterized road lanes. Sheng, take away whenever you're ready.
Hello everyone, can you hear me?
Yes, we can hear you.
Okay, and can you see my screen? Sorry, wait a minute.
Maybe I don't. I'll just give it 1 second.
Oh, I'm sorry, I don't have a camera here, so I just share my screen. Is that okay?
Yeah, that's okay.
Okay, now wait a minute.
Are you presenting?
Okay, sorry, I need to reboot this Zoom program and continue, okay?
I'm sure you move. So Sheng, we will just move on to our next one. Could you try to set it up in the meantime? We'll move to our next talk and come back to you.
Okay.
So Andrea, are you on the call?
Yeah, Andrea wanted.
Yes, I am. Can you guys hear me?
He wanted to play
Yeah, play the video.
the video. Yeah.
Yeah, can you guys hear me all right?
Yeah, we can hear you. So for our
so-
next talk, we are going to have a LION, which is LiDAR Initial Observability Aware Navigator for Vision-Denied Environments. Hopefully we hear some LION roars.
Yeah. Okay, so let me try to share my screen. Okay, I'll start by playing a clip of the presentation, and I'll be happy to take questions. Good morning, everyone. My name is Andrea Tagliabue, and today I'm presenting our work, LION, which stands. Can you guys hear the audio of the
Yes.
recording?
Yeah.
Okay. for LiDAR inertial observability aware navigator for vision-denied environments. This work was done in collaboration with my equally contributed authors, Jesus Tordesillas, Xiao Kai, as well as Dr. Ángel Santamaria Navarro, Professor Jonathan Howe, Professor Luca Carlone, and Dr. Aliaga. So this work deals with the problem of estimating the states for the robots that Team CoStar has used during the DARPA Subterranean Challenge. Team CoStar is a team composed of MIT, Caltech, JPL, and other universities. During the DARPA Subterranean Challenge, multiple robots have the task to explore unknown subterranean environments, such as tunnels, caves, or urban man-made environments like a subway station. And their objective is to identify the location artifacts and report them to a ground station. And as you can imagine, all these different conditions are characterized often by lack of illuminations or features, make state estimation a very hard problem. So specifically, vision-based state estimation approaches are challenging in this type of subterranean environment. As you can see from this picture, which shows an image captured by an RGB camera mounted on one of our robots navigating throughout the tunnel. And you can see as the robot moves, it leaves a big cloud of dust, which creates a strong reflection with the lights mounted on board of the robot, blinding the camera and making it impossible to estimate the state of the robot or track any visual feature from these images. For this reason, Team CoStar decided to adopt LiDARs as their main sensing solution for their state estimation strategy. LiDARs, however, are not perfect and they have their own failure modalities. And we identify one, which we call motion and observability. This happens when the geometry of the environment lacks of 3D features, so that it becomes hard to understand or estimate the motion of the robot. You can see an example of this issue in this video, where we are showing the point cloud recorded by one of our robots navigating in a corridor. And as the robot moves through the main direction of the corridor, geometric features disappear, making it really hard to understand if the robot is moving forward or not. In this case, for example, it's not moving. In this work, we will present then a strategy to enable state estimation using LiDARs for robots deployed in challenging subterranean environments, as you can see in this video, which represent one of the field tests that we perform where our algorithm has been deployed. And we will additionally present a strategy to detect geometric unobservabilities in the scene that may cause failures when using LiDARs for state estimation. And here you can see the output of our algorithms, which is represented by these 3 arrows, which encode how much each direction of motion is observable. So next, I will discuss the technical approach, which is divided in 2 main sections, sliding window estimator and the geometric observability detector. But first, I will provide an overview of the proposed solution, which is represented by this diagram. The main takeaway is that our method relies on the information provided by a LiDAR, as well as an inertial measurement unit. This data is pre-processed and fused sliding window estimator. The objective of this algorithm is to output an odometry estimate of the robot. This estimate is passed down to an algorithm called the resiliency logic, which has been developed in previous work. And the objective of this algorithm is to understand if the odometry produced by our method or any other state estimation methods available on the robot are reliable, based, for example, on the fact that some sensors may have failed or some algorithms may have diverged, and choose the output, the odometry estimate that is more reliable, sending it to the underlying autonomy stack. So this algorithm acts as a multiplexing solution for different state estimation methods. And in order to let this algorithm understand if our state estimate can be reliable or not, we introduce the observability detector, which again provides information on the possible quality of our odometry and state estimation estimates, allowing the resiliency logic to switch to alternative sensing modalities if the geometry of the scene does not allow to correctly estimate the motion of the robot. I will now describe the sliding window estimator that we use to produce our odometry estimate. The idea is that the sliding window estimator contains a state defined by the pose of the robot, the velocity, the gyroscope and accelerometer biases, as well as optionally the extrinsics between the LiDAR and the MU, so the relative transformation between the LiDAR mounted on the robot and the MU. So this diagram on the right represents the state used by, or the architecture used by our sliding window estimator, represented via a factor graph, where the blue circles represent the state, the green squares represent the prior information that we have on each state, and the red squares represents the measurement. And speaking of measurements, our factor graph relies on 2 main measurements. One is the relative poses computed from the iterative closest point algorithm, or ICP, from 2 consecutive scans, and you can see it added here, as well as the pre-integrated IMU measurement computed according to the algorithm described in this work. These measurements can be fused at 10 or 20 Hz, which corresponds to the rate at which the ICP algorithm is solved and computed. The temporal window of our sliding window estimator ranges between 3 and 7 seconds, a hyperparameter that can be tuned depending on the computation available on board. I'll now present the second component of our algorithm, which is the geometric observability detector. And the main idea is that we detect geometric observability in the environments by computing the condition number of the information matrix associated with the ICP. To summarize, the objective of this algorithm is to detect if the motion in the scene is observable and asking the rest of the autonomy stack to switch to alternative state estimator if the geometry of the environment does not allow to estimate the state using LiDARs. And the key approach is highlighted in these 3 steps. And what I would like to underline is just the following fact. First, we consider the point-to-plane ICP and its corresponding cost function, which is represented by this equation. Second, we linearize this equation, obtaining this second equation, and linearization is performed around the optimal rotation found. Once we have obtained this expression, which is again just the linearized version of this first expression, it is relatively easy to compute a matrix A, which is proportional to the information matrix and encodes the observability of the scene. And we can think of this matrix A as a sensitivity of the cost function with respect to x, where x represents in this case the changes in position or orientation. And we use the condition number of A to encode the observability. Another intuition is that the larger the eigenvalues of A, the bigger or the better is the observability of the scene. So I will now present an evaluation. First, I will show the performance of Lion in the context the DARPA Subterranean Challenge, specifically the tunnel competition, and then I will provide more details on the geometric observability detector. So in this video, you can see again the type of environment in which the robots have been deployed and in which the algorithm has been used. The output of Lion is also being used, for example, as input to the planning modules that you can see here. And again, here you can see the type of terrains and environments where the robots have been deployed. And as you can imagine, methods based on wheel odometry become extremely unreliable, as you will see also in the evaluation, because of the muddy terrain and the fact that the wheels can easily slip. So we first show an evaluation of the performance of Lion in the context of the tunnel competition by computing the root mean square error of its position, x, y, and z, and orientation, roll, pitch, and yaw estimate with respect to ground truth. And the root mean square error is plotted versus time, which is on this x-axis. We compare our method with 2 other solutions, which are the wheel inertial odometry, which is based on using the output of wheel encoder and fusing them with IMU measurement using an extended Kalman filter, and LOM, which is a LiDAR odometry method described in this paper, which does not use, for example, IMU measurement. And where Lion is used without the observability module in the context of this evaluation. And the ground truth is computed using LAMP, which is the global localization solution developed by Team CoStar. The key takeaways are the following. First, we can observe that the wheel inertial odometry is extremely unreliable, since the blue line, which represents wheel inertial odometry, quickly accumulates a very large error. This is because, again, the wheel slips a lot in this type of terrain. And the second takeaway is that, in general, the root mean square error of our approach is comparable to the one of LOM, performing slightly better in some conditions where Lion is represented by the red line, which is slower than the yellow line, which is represents load, and is better, for example, on the x, y axis and roll and pitch in this evaluation, and slightly worse on z and slightly worse in yaw. However, Lion presents some key system or field advantages, which are the fact that its output is gravity aligned thanks to the fusion of IMU estimates. It outputs the velocity of the robots, unlike LOM, as well as the extrinsic calibration. And its output can also be generated up to IMU rate, unlike LOM. Now I will present an evaluation of the observability detector. The evaluation is performed in an office-like environment, letting the robot navigate through a long corridor. And here you can see the point cloud capture different timestamps of this experiment. What we monitor is on the x-axis the time of the experiment, and on the y-axis the condition number computed by our method. And these images correspond again to the different time steps that are just snapshots, so time step 1, time step 2, and time step 3. And first, what we can observe is that throughout the experiment, so as the robot moves through this corridor and corridor presents a varying number of geometric features, the condition number changes a lot, reflecting again the fact that the corridor presents a varying number of features. And second, when we look at the values where the condition number is lowest, we observe that the scene presents a lot of geometric features, making the motion potentially easier to be estimated. And in the points where the time step where the condition number is higher, we observe that the scene does not present many geometric features, indicating that it's much harder to estimate the motion of the robot. So in conclusion, this analysis tells us that the condition number capture wells is an interesting metric to describe the geometric observability of the scene. And in this video, you can see the point cloud collected during this experiment, as well as the output of our algorithm which is now represented by these three arrows, which represent the eigenvectors scaled by the corresponding eigenvalues of the A matrix related to the translation part. And what we will see is that the higher is the geometric observability, the longer the arrows will be, and shorter, the less the observable. So now you can see that as there are some geometric features, this arrow has some non-zero length. But as soon as we enter in an area with a lack of 3D geometric features, the arrow associated with this direction becomes extremely small, almost invisible, and now it grows back because these features appear again. So by playing the video again, you can see some features, the arrow has some length. And then as we enter in this featureless area, the arrow becomes extremely small. Like the arrow represents the observability of the motion in this direction. And then it grows back. And last, I will present an evaluation of the performance of Lion when its output is used as input for the global localization algorithm. In this case, we combine the Lion with the observability detector. So what we can see on this plot on the left is an experiment performed again in an office-like environment, where a robot starts at this position and performs a loop in the indoor environment. And because of the lack of features that we observe in parts of the environment, the LiDAR estimation method accumulates large drift to the point that although the robot comes back in the real experiment to the original position, the algorithm, the global localization algorithm, estimates a drift of about 9 meters. However, when we use the observability detector in combination with the resiliency logic to switch to alternative sources of state estimation when LiDAR becomes unreliable, we can see that the error decreases a lot. So in this plot, you can see again that we repeat the same experiment, but the robot starts at the blue position and performs a loop. But the difference here is that our algorithm now realizes, our algorithm which initially used Lion as a state estimate for global localization, our algorithm realizes that the environment does not present enough geometric features for LiDAR-based state estimation, and switches to an alternative solution, in this case with inertial odometry, which is reliable in the indoor office-like environment, and then switches back to Lion. And this, as a consequence, we avoid to use LiDAR in this featureless area, and the overall error accumulated by the method is just of 1 meter instead of the 9 meters that we had before. And this enables the global localization algorithm to trigger a loop closure, which did not happen in the case before because of the excessive drift. And this again highlights the importance of the observability detector when in the context of the entire system. So in conclusion, we have presented a local state estimation method, which enables a high rate and continuous and smooth output. And this state estimator has been used in the DARPA Subterranean Challenge tunnel competition in combination with a global localization solution LAMP described in this paper. This algorithm has been co-designed with a supervisory algorithm in Bind, which is the resiliency logic, or called HERO, that I described before, and more details can be found in this paper. In addition, we decided to use a loosely coupled and non-feature-based approach for the following reason. First, there is a computational advantage because feature extraction is in general computationally expensive, and it is possible to share the computational cost associated with performing the ICP algorithm, for example, by reusing the output of ICP for other algorithms. Additionally, not using features allows us to have less priors on the environment, making the method potentially more generic. So with this, I've concluded, and I'm happy to take any questions.
Thank you, Andrea. So, any questions from the audience, or even the virtual audience? I guess if not, we are really running over time. I'll just ask a quick question. When you're doing the observability detection and then switching controllers, how do you handle any discontinuities that you would get from your different sources of odometry?
Yes, so I believe this is taken care internally by the resiliency logic, which modifies the reference frame of the sources to take that into account. So it transforms. I believe that what changes is the goal for the controller rather than changes the state estimates. So that frame gets updated. So the discontinuity is pushed into the reference position for the controller, for example, rather than having a jump in the state estimate.
Mm-hmm. All right, thank you.
Yeah.
All right, thank you, Andrea. We'll move on to our next speaker. Again, Sheng, are you ready with your slides?
Yes, I'm ready now. And
okay.
Can you see my screen this time?
Just give us 1 second.
Hello, can you see my screen this time?
Just 1 second, Sheng. Yeah, now we can see you. Can you put it in presentation mode, please?
Okay. Sorry for the interruption, and now I will begin my presentation. Hello, everyone. This is Shen Yang from the Autonomous Driving Lab of the Alibaba Group. And in this talk, I will briefly introduce our paper entitled Visual Semantic Mapping and Localization Using Parameterized Row Lanes. The most widely used two types of maps as built from different sensors are lidar maps and regional maps. The most important attributes for different entities in these maps are geometric and semantic information. A lidar sensor directly output the 3D position of obstacles, whereas for cameras, we need to additionally perform feature detection and triangulation to recover the depth of target pixels. In recent years, the visual STEM community has released a bunch of useful primitives that can be constructed into the map. These primitives include corner points, lines, boxes, and even quadratics. And they are often extracted and described by either handcrafted features or deep models. These primitives are designed to represent their corresponding suitable objects in the real world. So for practical localization scenarios, we need to first figure out what are reliable features we can use during on-road localization. And then we need to judge whether those commonly used primitives are sufficient and also ease of use. The most prevalent installation style for cameras in this scenario is to stick them onto the front window and to generate a front-facing view for driving vehicles. And here are some pictures taken from such front-facing cameras. From these pictures, we can see that most images contain a large area of roads on the ground. And these roads are often painted with lanes and ground signs. And moreover, we can also rely on other traffic assets such as fences, lampposts, and the rest part. So we should also evaluate whether we can rely on these movable things. Although in short-term localization, we can extract reliable features on cars and bikes to perform short-term localization, but it is better not to construct them into a persistent map for a long-term use. So far, as we have discussed those candidate features, and here comes the core problem, which our paper is facing, that is how to parameterize those frequently observed road lanes, because they have taken in a major part of what we can see from the front view. And because lanes can everlastingly expand along the road, we would better choose a piecewise form that is adaptable to expand continuously. Should we choose the simplest way that breaks the lane into multiple straight line segments, or develop a parameterization method that can easily depict bend rows and terms? So the answer is the latter one. And here is the comparison of different parameterization methods. The first column is to use piecewise line segments. They are first order functions, and the latter two columns are for candidate high order curve segments, such as Bezier and Camus-Roux splines, respectively. And we have listed several properties of these representations to discuss their strengths and weaknesses. Green for the good, those green ones for the good aspects, and the red one for the bad aspects. The first row compares control points that define the shape of the curve. If control points coincide with the curve, it would be easier to initialize their location through the random sampling once we have a coarse 3D samples of the curve. And the second and the third row is the ability to describe a diversity of row shapes. If we use line segments, we need to provide those dense sampling on terms and design strategies on how many points we need to sample concerning the local curvature. So we need to consider how to merge and split this control point if these line segments are not fitting well. As an alternative, instead, high-order polynomial curves can use fewer control points, and the curve continuity here in the table means the smoothness of the shape, where C1 means their first-order derivative is continuous, and C2 for the second-order derivative is continuous. And we have surveyed a bunch of applicable curves, more than Bezier and Camus-Roux, and figured out that a cubic polynomial curve can either have C2 continuities or those control points lied on the curve. So we can choose only one character. We can choose only one character. And through considerations, we think the C1 community. We think the C1 continuity is more important. So we choose the cubic Bezier So we choose the cubic Campbell room as a proper form of depicting road lanes. And here comes another question. The perspective projection of such a high-order piecewise polynomial shape onto an image is no longer a polynomial function. In other words, when we want to construct a pixel-to-curve residual, as the green notations have shown, we must iteratively solve the curve parameter t here to get the actual residual. This is a major difference from using line segments and high-order curves, because for the line segments, we only need to find out the closed form of the perpendicular feet of each valid piece and then choose the nearest one. So we now discuss how to construct an optimization problem by choosing such a piecewise Catamount room spline. For each 4 continuous control points, they depict how the shape looks like between the 2 middle control points. The 4 times 4 basis matrix that appears in the definition is the code definition of the Catamount room. By changing such a basis matrix, we can switch to other curves such as Bezier or B-spline curves. The mass node tau here for the Catamount room category is the tension that depicts how such a spline sharply bends at these control points. And then our bundle adjustment problem for optimizing such curves mainly uses 2 residuals. The core residual is the pixel to curve cost as the second equation. But we need to explicitly define an optimizable variable t here as the TACI here, individually for each residual, because as we have talked about in the last slides, we cannot write a closed form to eliminate such t during the construction of such cost. So we need to solve a quintic equation, the 5th degree polynomial equation, to have the initial value of the t and perform and to jointly optimize such curve parameter t in an expectation maximization manner. Another residual is the ground assumption cost by assuming a static extrinsics between camera and the ground. Our system is based on the assumption that the driven ground can be regarded as locally planar within a depth cutoff range of each view, maybe 30 or 40 meters. So we can use the reground intersection to initialize 3D samples and curves and add the regularization term as the third equation to constrain the height range of curves. This locally planar assumption for the ground is practical and useful for monocular SLAM because we are often lack depth information without additional parallax views. And finally, we briefly introduce our systematical modules to bring up the optimization problem during mapping. First of all, we adopt a lane net published by Nevin et al. To percept the lane contours as sampled pixels. Then in the front-end tracking module, we can use homography to establish the lane-wise association and split the left half contour and the right half contour to track them individually. Specifically for dashed lanes, we can use their corners because they can perform pixel-wise tracking and to enhance the robustness to the curve optimization. For methods about how to initialize our control points, please refer to our paper. Here shows our demo of semantic localization in comparison to a point-based localization. The right part is our proposed method with road entities. It contains orange road lanes as presented in this paper and some other semantic features as presented in our RAL 2021 paper. We just use all the methods described in this paper to construct this orange road lanes, including these solid lanes and dash lanes. Compared to those point-based methods, we can build a more meaningful semantic map for the large scenes, and it can be more compact, and all the landmarks will be frequently searched and used. Will have a higher frequency of use. And we also need to point out that in the practical use of these lane features, we suggest using them together with other applicable features, because purely used lanes are suffering from these two degenerate cases: long straight lanes and fixed curvature terms, such as circles and rings. Dashed corners may help to localize, but as all lane features are located on a quasi-planar ground, we suggest adding some underside features or undersky features, such as poles and buildings and those traffic signs, to robustify the state optimization. And thanks for your listening. We also refer you to our latest paper published to the IL and ICRA 2021. Which is rather a system paper of our semantic mapping and localization solution on the road. If you've got any questions about these two papers, please feel free to contact me by my email from here. And that's all for my presentation. Thank you.
Thank you. Any questions from the audience here or virtual audience? You guys are making it difficult for me. So I have a couple of questions. Great talk. So in your degenerate cases, right, you said about using other kinds of long-term consistent features.
Yes.
How does it scale? Like, one question is, how does it scale with, as your feature, let's say you add more and more features, such as other highly compact features on the road, let's say signs and other things. How does your algorithm scale with that?
As we have discussed in this page, sorry, I need to find out the page. As we have discussed in this page, these are all the features we have considered to use during on-road localization. And lane, we have talked about in this paper how to construct it. And for the rest of features, we think that ground signs, just those arrows painted on the ground, and those traffic signs beside the road or just on the sky, they are very reliable features, and they can hardly be occluded by other cars and vehicles. So we just perform semantic detection or segmentation on each image, and to extract deep features or handcrafted handcrafted features. Either are okay. And after we have extracted handcrafted or deep features on those semantic meaningful objects, and then we can perform a full semantic mapping on those all reliable features, so that we can have a persistent map that is robust to the weather or seasonal change.
Okay, I think on the similar lines. So let's say if you're just tracking the curves, the Catmull curves, how large is your feature vector? Let's say at any instance, and so you have like let's say for 5-lane road, so you're just tracking 5 basically curves along the road. In this case, let's say,
Yes.
yeah, how many features are you, let's say, tracking at the same time, and how would that scale up once you have more and more? That was my original question.
Okay, on average for each image, we just use 3 or 4 half lanes. The half lanes means the left side contour or the right side contour of each lane, because it has a contour, and the contour will be more precise than the center of each lane. And then after lane, we just use those commonly observed poles and just those ground signs, as we can see from this video demo. And they are about 3 or 4 on average per each image, because they are not often observed. They are casually on several images, so that's just the average number.
Okay.
In case we have, yes.
No, I think that's good. Yeah, made it clear. Okay, thank you very much again, Sheng. We'll move on to our next speaker. Thank you again. So the next talk is yet another DARPA sub-T. It's by John G. Rogers. So the title is DARPA sub-T Urban Circuit Mapping, Dataset, and Evaluation Metric. Carlos is just going to set his laptop in case John has some network issues.
Let's see, it's telling me I can't start screen while the other participant is sharing. Okay,
Oh,
let's
yeah.
see if you, can you unshare, please? Okay, there we go.
Oh.
All right. Can you confirm that you can see my slides?
Yes, go ahead.
Good morning. I am John Rogers. I work for the Army Research Laboratory in the United States, and this work, entitled the DARPA Sub-T Urban Circuit Mapping Dataset and Evaluation Metric, was put together on behalf of DARPA by my colleagues at the Army Research Laboratory. So part of my duties in working with DARPA on the Subterranean Challenge were to provide benchmarks and evaluation metrics that we could use to look at robot mapping algorithms in these subterranean rescue situations. So as many of you are probably familiar, the DARPA Subterranean Challenge consists of 3 subdomains: the tunnels, the urban underground, which this talk is going to focus on my data set collected at the urban underground, and the cave circuit, which was unfortunately canceled due to COVID. And we have just finished the finals challenge, which there will be another data set forthcoming that looks at that challenge circuit, that challenge environment. Briefly, my work is focused on the evaluation of SLAM algorithms, simultaneous localization and mapping, as I'm sure all of you are familiar. SLAM is a technique for robots to localize themselves in the environment or determine their trajectories, while simultaneously recovering a map of that environment, which can be used for navigation. Typically, in modern implementations, this consists of smoothing a graph of measurements of features or landmarks or relative poses of robots as they move along their trajectories. In the urban underground circuit, the course was built inside the abandoned, incomplete nuclear generation plant in Washington State, United States. This facility has 1 out of 2 reactor buildings constructed, but never featured any of the heavy equipment and reactor cores or anything like that. In the main reactor building, which the 2 alpha and beta courses were constructed, there's a central chamber which would have been the location of the reactor core. And as you can see, each of these courses has this circular region in the middle, which was the reactor core, and they consist of, each course is 2 levels in the reactor building, which I believe is 7 stories tall. So there's a total of 3 stories that are this course, and 2 of the levels partially overlap, but were separated by physical blockades. We used our robot systems from the Army Research Laboratory to collect the data sets in these courses, and to handle the specific challenges in the urban circuit, which consisted of a number of stairways that had to be traversed. I've used a iRobot PackBot Explorer with flippers that enabled me to drive down the stairs to some degree of success. And on board this robot, we collected data from Ouster OS-164 LiDAR, as well as the Carnegie Robotics Multisense SL Stereo and LiDAR. This was also used to provide illumination so that the artifacts within the course could be detected. On board the robot, we also use a MicroStrain 3D MGX 525 IMU. Thanks to the efforts of my colleagues at MIT, we were also able to bring in a quadrotor robot to collect an aerial version of the data set as well. And here is an image of it. It consists of a RealSense D435i, and therefore it's only collecting a visual data set, and it does not have any onboard illumination. The DARPA Subterranean Challenge entrance portal consists of a series of localization fiducials, which are used to establish a global frame of reference. So the first part of each of the ground data sets that I have provided here will feature observation of these fiducial landmarks to establish this global frame of reference. In the DARPA Subterranean Challenge, points can be scored when artifacts are located within the environment within 5 meters of accuracy. So anything within 5 meters of absolute global position as compared to a ground truth state will result in scoring 1 point. In our evaluation, we also record the minimum error that a landmark is detected, the maximum error that we report a landmark, as well as the composite root mean squared error of all artifact detections. In this work, we also introduced a relative root mean square error metric that can be used for the aerial data sets, which don't feature observations of the initial fiducial landmarks for global localization. Points are scored in our data set by providing the solution to the ROS-TF system in the following way. When artifacts are observed within the data set, I have encoded them. So first of all, the robot receives this global frame alignment from observations of the fiducial landmarks at the beginning of the run. Then secondly, I have encoded the location of the artifacts within the environment. Here, the vent artifact is seen observed. I have an interface that allows me to click on this and generate a relative measurement from the robot to that artifact during a coding run that records an auxiliary file that can then be played back during a mapping analysis run. And during the mapping analysis run, the mapping system under test will provide the missing transform between the robot start frame and the robot's current location at the time of the artifact sighting. By composing these transforms, a global localization can be computed for the artifact and it can be compared to ground truth. Here are some videos showing the shape of the dataset courses. Here you can see in the alpha course, we have the first run consists of just the first floor of the alpha course. And then the second run consists of, here on the right side, consists of starting out in the first floor and then going down the stairs into the second floor. And on this side view, you'll be able to see when the robot drives down the stairs to collect that second floor portion of the data set. There were 2 courses at the DARPA Subterranean Challenge Urban Circuit, and the second course is the beta course, which is quite a bit more difficult. It is 2 floors below the alpha course and consists of an initial very long hallway, which provided some challenges for mapping algorithms in terms of visual aliasing. And much later in the course, you can see right here, that's where the stairway is. So you have to drive all the way down that long corridor before you go down the stairs. And here in the second beta 2, we go down those stairs and into the second floor. And this video will show the side view to see what that looks like. Here you can see the stairway pretty well. Yeah, there's sort of 4 stairway segments in each of these down traversals. These floors are quite tall. In addition to the ground data sets, we have 2 new visual data sets collected by our quadrotor kind of focused on portions of the course that are very well lit. Lighting was an issue for the visual SLAM algorithms we evaluated. So this had to be limited to shorter sections where there is much more light. Here's the alpha course. You can see it's brighter overall. And then the beta course is quite a bit darker. And this is the most well illuminated section of that course, which is still quite dim. So in our initial evaluation, we also tested a number of existing SLAM algorithms, starting with our own implementation of OmniMapper, which is released here on GitHub in our open source version. This is actually the version we use in the Army Research Laboratory and in the Army Research Enterprise for performing LiDAR-based SLAM. We also evaluated Cartographer from Google, Lego Loam, which includes a loop closure component, and we also looked at how well the system would do if we just integrated the odometry on the platform and didn't perform any sort of SLAM operation. For the aerial robot, we were able to use several visual SLAM techniques, Orb SLAM 2, MSCKF, and Chimera. So here is a large table with many of the results from this experiment, but in general, I have a couple of observations that I'm going to present here. The alpha course, Alpha 1, was the easiest of the 4 ground robot courses. And that was because it featured mostly planar motion and didn't involve any stairway traversals. And it involved a lot of larger open spaces where the LiDAR-based SLAM was able to make observations with long range. In the Beta 1 course, the robot had more difficulty with a long initial corridor, which in Cartographer especially, if we ran it without odometry, it suffered from bad aliasing down that corridor and resulted in very poor localization. The staircase sections were very tough in general and very hard on the robot system because I actually literally put the flippers down and then drove down the stairs and tried not to flip over. During this, the sensors on the robot suffered some damage, and there were some issues with the ouster portion of the data sets. So due to that, on Beta 2, for example, only the OmniMapper and odometry results are available because the ouster was damaged during the stairway portion, and OmniMapper was able to function on both the LiDAR cloud that comes from the ouster, as well as the cloud coming from the Multisense SL, which is a spinning Hokuyo LiDAR scanner. In the aerial portion was the only time we were able to perform visual SLAM. Initially, our intention was to perform visual SLAM as well on the ground data sets. However, the illuminators were much too dim and the frame rate was much too low to successfully perform frame-to-frame matching of features for any meaningful length of time during the ground robot data sets. Visual SLAM was only useful during portions of the aerial data sets, which we sub-selected. And due to that, the entry portals were not visible in the aerial data sets. And so only our relative metric was available. And I haven't discussed the relative metric, but you can check the paper for details on that if you wish. And I'd like to point out that the numbers and results here are kind of a current snapshot and based on our evaluation without any special tuning or careful adjustment of these specific SLAM algorithms to perform well on these data sets. And the visual techniques especially would probably benefit from a more extensive tuning effort. In the future, we're going to be providing the DARPA Subterranean Challenge Finals test set, which will consist of multiple runs in the course that was just completed in September of this year. And here's sort of a bit of a preview of that. We also have a new mapping analysis metric, which was provided live on DARPA TV, DARPA Sub TV, which gave you what the coverage rate is, as well as the deviation from a ground truth point cloud. So we can take in the point clouds that are coming out of SLAM and evaluate them directly against a ground truth point cloud. And so and now I would take any questions you have and invite you to take a look at these data sets and evaluate your own SLAM algorithms as well. Thank you.
Thank you. We have time for 2 questions. Anyone from the audience this time? Online, anyone? Okay, I'll go ahead. First question, I guess it's a really good work with the data sets. It's usually helpful to test your SLAM algorithms. How did you solve the challenges with calibration? You have like a spinning 2D LiDAR with multiple cameras, multiple IMUs, or is it, how did you tackle that challenge in that?
Yeah, that's true. Calibration is an issue. On In the data sets themselves, we have the ability to update the calibration. If it turns out to be a problem in our evaluation, it didn't seem to be too much of a problem. We did run caliber for the visual portion on both the air and ground data sets. So we have the IMU and camera positions, but it is possible there could be some error there. But we have, like I said, through the use of the TF system, we're able to pull out the calibration and put in new calibration for the extrinsics of the other sensors if it were a problem.
Okay.
However, the calibration, I believe, was done with sort of looking at planar alignments of the two LiDARs and making sure that they agreed on the shape of like a cubic room, for example, make sure that they were aligned well.
So this was pre-calibrated and you didn't have any online sort of calibration?
That is correct,
Okay.
yeah. But like I said, if anyone has a problem with the calibration, we can substitute in a corrective term later.
And then one final question. In your comparison results chart, you had MSCKF. Did you... oh, sorry. Well, great.
Thanks. John, thank you so much for your data sets. Chris Ekman, University of Colorado, we've looked at them a lot. And so I was curious when you mentioned about the illumination, seems like that's like a very challenging thing to work with because you have so many different illumination settings and different ways you can position your lights. And this is going to be an ongoing issue, I think, for any kind of visual methods in actively illuminated environments. I'm wondering if you have any insight as to what you considered when you were choosing your illumination and whether or not there are any solutions for maybe variable illumination or anything like that you might shed some light on.
Yeah, I think the participants in the challenge did a very good job of providing illumination on their robots. And I think that that's probably where you should look for insight. In my case, I didn't have a lot of time to specifically address illumination. So we just used what we had lying around, which was the Multisense SL with illuminators, and it really wasn't sufficient. So, but if you look at some of the robots that actually did well in the challenge, you'll see that they have quite a bit more illumination and a broader field of view.
Yeah, the trouble is that many of them, I think none of them actually used visual odometry or any kind of visual SLAM methods. And so essentially what you're saying is, there's probably no solution that is out there or has been figured out yet for using visual methods for these kinds of environments.
Yeah, I think that visual methods right now are, kind of confined to outdoor, brighter, illumination conditions, and they're not probably ready for subterranean. Yeah.
Yep, great, thanks.
We'll move on to our next speaker in just 1 second. Thank you.
Thanks.
All right, so our next speaker is Christoph. He'll be talking about experimental validation of energy optimal turning radii for skid steer rovers. Christoph, whenever you're ready.
Great. So could you hear me and see my slides?
Yes, perfectly.
Great. My talk is a little different from the ones we've seen so far in this session, where we've been looking more at the planning of paths for skid steer rovers. And the skid steer rovers are often used in many field environments here on Earth. For my lab specifically, we're interested in skid steer rovers for planetary environments. There are multiple missions planned right now for sending micro rovers, skid steer rovers, to the moon. And they're very robust and useful robots. One of the challenges with skid steer robots is the amount of power that is required to actually perform a turn. So there's been work in the past in the literature looking at how the power consumed by a rover is related to the turning radius. So for a skid steering rover, for example, tight turns require much more instantaneous power than broader arcs do. But of course, one of the other things that we really care about is the total energy consumed. And the energy consumed is, of course, the integral of power over time. So we also don't want to take such wide arcs that we extend the path so much that in the end we lose any savings from the lower power. So in our work, we evaluated a few different approaches, namely driving in circular arcs and lines versus point turns and lines. So point turns and lines are a very popular operating mode for skid steer rovers, as sort of the planning aspect and the execution aspect is very simple. But we compared these two circular arc and line combination trajectories. And in particular, we looked at, we found that there's one turning radius that is a key reference point for us, which we called R prime, which is the turning radius that's achieved when the inner wheels aren't turning. This is defined as half of the rover's slip track, which is a term that has been defined in the literature in multiple papers. So we found that R prime is really important, especially on hard ground. So when you're operating the rover indoors or on hard surfaces, rocky surfaces outdoors, then we found that turning at R prime is the energy optimal way to operate a skid steer rover. So what we see on the right here is an energy comparison between CLC paths, so circular arc line, circular arc paths, and the sort of baseline comparison PLP paths. So PLP paths are the reference point at 0 here. And then on the y-axis, we have the amount of energy saved by doing a CLC path relative to that PLP path. The negative numbers show savings in energy. And we tested this at different turning radii. So where 1 refers to R prime, and we see multiples of R prime, so up between 0.4 R prime and 1.8 R prime or so, in terms of turning radius. We see that we see the most energy savings on the order of about 10% energy savings for about a 10-meter path when we make these turns at R prime. So we also tested, we did experiments out in the field in loose soil, and what we discovered is that we could still save energy by driving CLC paths relative to PLP paths. We could still save about 10 to 20% of the total energy over the course of the path. But we need to take slightly wider turns than R prime turns. We found the optimal to be somewhere between 2 and 3 times R prime. And we actually found that around R prime itself and below R prime, there were cases where it cost us more energy than driving point turn and straight lines. We investigated that, and we found that there are a couple of factors that lead to that. One of them is that when you're driving at R prime, the inner wheels aren't turning, so you're basically dragging them through the soil, and you can experience this sort of bulldozing effect, pushing through loose soil when you don't have the wheel spinning. And actually right below R prime, to achieve a particular turning radii, the skid steer rover is commanded such that the outer wheels are driven forward and the inner wheels are driven backward. So at a point turn it's doing that, but at any turning radii between a point turn and the R prime, it's also doing that. But because of the skid track, slip track of the rover, those wheels, despite being turned backwards, are being dragged forward by the overall motion of the robot. So you can have situations where the wheels are rotating backwards, excavating soil out in front of the wheel, and then being dragged through that pile of soil. So these are some lessons learned in terms of operating these skid steer rovers at various turning radii. Now, we developed a system using optimal control and Poitras-Hagen's minimum principle to figure out the actual optimal trajectories for traveling from a particular starting point to a goal. So what this chart on the right shows is it's a color-coded map in XY space, starting at a particular angle, pi over 4, and trying to end up at the origin with an orientation of 0. And the color codes show the type of path that is optimal using these optimal control techniques from getting from this green dot, which is sort of in that XY space, to that origin, which is denoted with the yellow star. So in this particular case, we're in the royal blue area, and our analysis shows that CLC paths, or circular arc, single line and circular arc, is the optimal way to get from that green point to the end point. This takes up the vast majority of the space. The other sort of major areas that take up significant portions of the space are this orange and dark blue. Orange is a CLCC path. So you see here, starting from this green dot, to get to the origin, you would need to first do a circular arc, line, and then 2 Cs in sort of a cusp, 2 circular arcs in a cusp-like shape. And the dark blue is sort of the skew symmetric of that, where you do CCLC. So these are the types of paths that we found to be optimal depending on where you start relative to your goal. So essentially, if the goal is more or less ahead or behind you, you want to do CLC paths. If it's sort of off to the side, then you need to add this additional circular arc, which makes it a little bit more like a parallel parking maneuver. So we also tested these CLCC paths experimentally and found similar results where around R prime, we had sort of additional energy costs. So we want to avoid that, but we can save energy relative to PLP paths, again, on the order of 10 to 20% of the energy, with operations, circular arcs around, in this case, 3, maybe even a little more times R prime. So summarizing these results, we're able to save anywhere from 10 to 20% of energy for skid steer rovers when you're operating sort of on the medium scale for individual waypoints, say, maybe 5 times the rover length, 5 to 10 times the rover length. We could save relative to point turn operation using these arcs. And the most important class of these types of paths is CLC, but also CLCC and CCLC are other important ones if your goal is a little bit to the side of where you're starting. We're currently working on developing ways to integrate this seamlessly into an operational context. So developing what are the sensing requirements and what are the initial field testing requirements in order to do that. And we want to develop plans that we can implement in real missions, including a comparative analysis of optimal plans to sort of baseline PLP plans in an actual lunar mission. The Canadian Space Agency is working on developing a micro rover, skid steer rover, for a lunar mission planned by about 2026. So the bottom line for energy efficient skid steer path planning that we found is that if you're driving on hard ground, you want to make turns, you want to make R prime turns, assuming you have the space to do so. And then you want to get as close to R prime if you can't make R prime turns. But if you're on granular soil, on regolith and things like that, you want to actually avoid turning right around R prime, so anywhere between, say, half of R prime and 1.5 times R prime. And you want to turn, if you can, if you have the space to do so, at about 3 times R prime. That's energy optimal, we found, in the loose soil. And if you don't have the space to do that, then doing a point turn is probably your next best bet. There are ways to use these CLC paths and CLCC paths in specific contexts. If you're starting with a global path that has waypoints and just sort of lines connecting them, one way to do it is to choose this optimal turning radii and just sort of round off your global paths using that specific turning radius. But you can also use these CLCCs and CLC paths directly, such as, here's an example where you're facing something that you're inspecting with a rover, and then you want to move on to another waypoint, and in this case, a CCLC is a very nice and energy efficient way to transition towards that. If you're driving along in a straight path and an obstacle, you discover an obstacle ahead of you, that doing a combination with a pair of CLCC paths with a new waypoint to the side of your obstacle would be an energy optimal way to operate in this particular setting. And with that, I want to thank you for your attention and be happy to answer questions if there are time.
Thank you, Chris. We have time for one quick question. Okay, Chris, great talk. So have you thought about, like right now you said like the solid surface versus the loose gravel, is there a way to detect it using your torque feedback that you can have an adaptive R that you can choose? Are you thinking about that long term?
Yeah, that's a great question. And that is something that we're looking into and interested in. So terrain classification using the feedback from our sensors, including the power that we are measuring, from motor currents and things like that. So yes, we don't have results to share on that yet, but that is part of our long-term plan. It's a great question.
All right, thank you. Thank you, Chris. All right, we'll move to our final speaker, Adam. You're online, and then the talk is about online soil classification using a US sensor emplacement system. Adam, take away whenever you're ready.
Okay. Good day. Let me see, I'm going to share my screen for everyone.
Great.
And presentation mode. Okay. Can everybody see the screen?
Yes.
Okay, excellent. Good day, my name is Adam. I'm from the University of Nebraska in Lincoln. I work in the Nebraska Intelligent Mobile Unmanned Systems Lab. We are the university's robotics lab, essentially. Mostly work with aerial vehicles, although we're venturing into some rover-based things here in the future. For the next 12 minutes or so, I'm going to talk to you folks about estimating soil moisture content and soil compressive strength from a drill, essentially a drilling system that's mounted on the bottom of a drone. I'll show you a quick video to kind of motivate the discussion. We have a system that's on an DJI octocopter. You can see on the bottom here, there's a rather large system attached. That is a drill, essentially. And what we do is we have an auger, or basically a giant drill, but that's hollow. And we drill that into the ground, and then we leave it there. and the drone flies away, and we leave a sensor inside the soil. And this is what that looks like. Basically, it's a hollow plastic 3D printed auger, and you can put whatever sensor you want in there. For our research and our project, we're less concerned with what the sensor is. Our sponsoring agency was more interested in our ability to put a sensor in the soil. But if you want to know why you would put a sensor in the soil, one of the best examples would be a seismic sensor, where you want to have a very tight physical coupling to the medium that you're measuring. Other things that you can do in the soil are sensors that actually analyze the soil itself in terms of chemical or mineral contents. We can have airborne particles that come down to the ground. You could have a sensor and leave it there. It has a benefit of also being unobtrusive, and that wildlife or passerbys aren't going to necessarily confound your data gathering attempts with your sensor. So that should give you an idea of why we want to put a sensor in the ground. The main challenge, though, is actually drilling the sensor into the ground. Typically, when you want to drill something into soil or any other medium, actually, the solution is to add more weight or push harder on the bit. We call that weight on bit in the drilling community. Or add power to the motor itself. We don't have that ability necessarily because we're on an aircraft and we're constrained by the weight that the aircraft can carry. Right now, I'm pretty much at max gross weight on the aircraft system. So if I were to add more weight in order to be able to dig better or add a larger motor, I wouldn't be able to fly anymore. So we're kind of stuck where we are. We need to find an optimal way to use the thing that we have with that augering system. Some other things with soil itself, it's very random, at least from the perspective of the system as it drills. We don't know what the next layer of soil is going to contain, especially with impediments like rocks or roots. We've run into animal carcasses a few centimeters under the soil. That was interesting. And we find from some previous work that we've done that with our augering system, soil moisture content and compressive strength drive the difficulty of digging evolution. Soil moisture is essentially just how much water is in the soil mass itself, and compressive strength is a measure of how much force is required to displace the soil from its current position. That's measured in kilograms per square centimeter. So the thing about understanding those two parameters of moisture content and compressive strength is they allow us to change the way we dig. Different soils require different techniques with our limited system in terms of the amount of weight we can add, which, by the way, I can only push downward with about 11 kilograms of force when I dig. So I have to use different techniques in digging. One of the main ones that we use is called pecking. A peck is when you have an auger in a hole and you pull the auger out of the hole and you allow the accumulated material that's in the flutes. Those are the helical coils that wrap around the shaft that transport the material out. In some cases, they get clogged, especially in wet soil. So when we peck, we pull the auger out of the hole and we allow that material to fall free. And then we can put the auger back down the bottom of the hole and allow for more material to be brought up those flutes. We also adjust how hard we push down when we dig. Like very hard and dry soil, we don't want to push down as hard. We want to use a lighter force to allow the tip of the auger bit to essentially break up that soil and then transport up the flutes. We can also change the rotational speed. So these are techniques that we can do, but we have to understand the soil properties first. And if you're wondering why we can't just directly measure these properties, I can't add more things to the aircraft already. In order to measure soil moisture, I would have to use, in this case, what we would call a capacitive device, which is you essentially stick two probes in the soil, measure the amount of electrical current flows between those probes, and you can estimate your soil moisture. The problem is I want to know what the soil moisture is at any given point in that column of soil. So I would have to remove the auger and place a probe in there. I can't do that mechanically on the system that I have. And the same holds true for compressive strength. That is measured with a device that essentially is a strong spring with a probe that you push into the soil. And I don't have a way to mechanically actuate that. So I need to find a way to understand the soil moisture content and the compressive strength without direct sensors. So why is all of that necessary? The idea is that everything on my aircraft is autonomous and battery powered. So I need to be able to get my sensor into the ground efficiently, or I need to be able to pick up and move to a new location. With each augering evolution takes about 85 to 90 seconds. I want to know fairly soon if I'm going to succeed or if I need to change the way I'm drilling. So it's important that we do this with some rapidity. Here is the system itself. We basically have an elevating platform with a drill on it that is controlled by an Atmega processor. It's not shown here in the pictures, but we can move that elevator up and down fairly quickly. We have a brushless DC motor that controls the auger itself. And we have various sensors on board, and those sensors become important in terms of understanding the environment and then feeding that into various machine learning algorithms to kind of estimate the soil properties. I'll talk about the actual sensors in a moment. For the experiments that we ran, we did a little bit of indoor testing, and some outdoor testing was the predominant method of operating. You can see in the pictures here, I have the system mounted on an aluminum frame. It's not on an aircraft. That's for testing purposes. I can't always just fly all the time. And when I'm accumulating a lot of data, it's easier to just have that on an aluminum frame, as you can see. Measured in various parts of the United States over the course of this work. And I would take telemetry data from the drilling system, and I would also do manual measurements of the soil properties at 3 points in every hole I dug. So I would measure the soil moisture content and the compressive strength at various parts of the hole, so I would have a ground truth to use for the training and my algorithms. So out of the 150 trials I did, that means I had 450 soil measurements for moisture and 450 for compressive strength. The moisture ranged from 0 to 80%, so very dry to very wet. And the compressive strength ranged from 0.2 kilograms per cubic centimeter up to 4.6. To give you some more human understanding of what that means, 0.2 kilograms per cubic centimeter, you can take your finger and push that into the soil pretty much arbitrarily up to whatever depth you want on your knuckle, so to say. At 4.6 kilograms per cubic centimeter, if you touch that soil, it's going to feel like a rock. You can tap on it and it will sound like a rock. Eventually you'll be able to dig through it, but it's very hard. We also then sampled the parameters from the digging system itself at 10 hertz. So over the course of the experiment, we generated about 2.8 million individual data points that we were able to analyze. So to classify the soil moisture and the compressive strength, we essentially evaluated numerous machine learning algorithms. These are all statistical based. We didn't do any deep learning for this particular work. We found when we used Gaussian process regression, we actually got the best results. So in terms of the feature set that we used for the predictive algorithms, we used the motor current of the auger. We used its rotational RPM. We knew how much time we spent digging. We were able to measure how far down we were. I have strain gauges on the system to allow me to know how much weight I'm using on the bit, so how hard I'm pushing down. And we also use accelerometers in the X, Y, and Z axis to measure vibrations. This actually helps with finding foreign objects. Like if you hit a rock, you'll get a very massive spike in a couple axes on your accelerometers. So we would use these as our feature set and apply it to the various algorithms. These two graphs show kind of visually what digging looks like, or what drilling into the soil looks like. On the top graph, if you look, the green diagonal is a linear trace of depth as we go down. The black line on top is the auger RPM. We try and maintain a constant RPM, so that's a controlled state, but we do allow RPM to drop as motor amperage increases. And you can see that on the green line at the bottom. As motor amperage goes up, we saw some RPM dropping. So those are what we measure, as well as the weight on bit. And then at the bottom, you can see we measure acceleration in the axes. So when we ran it through all of the algorithms that we chose to try, we found that the Gaussian process algorithm, the regression scheme that we use worked very well. If we look at the 30-second mark, we were actually very accurate. Now, in terms of accuracy, what I mean here is how close our estimation scheme was to the actual measured values on the data that we didn't use for training. And in terms of the training data, I actually used about 50 of my 150 digs for training, and then we compared against that for the actual testing. So we find that Gaussian process regression as a multivariate regression problem in this particular case worked very well for us. So for the future work, the idea is to take our soil estimation and can consult that in real time as we dig, and then apply it to an adaptive capability to change the way in which we drill into the ground. Because you can imagine as you start out in dry soil, as you go downward, you may hit some wet clay, and you're going to have to change the way you dig at that point in order to effectively and efficiently get your sensor into the soil. And we may look at some deep learning. I'm not sure where that's going to go at this point. So I will conclude by saying that drilling from an unmanned aircraft system is a unique problem, and it's very challenging, but it can be done. And we do find that certain machine learning techniques give us very useful policies for classifying or regressing through the soil in terms of its moisture content and compressive strength. We use the sensors that are on board the aircraft to estimate this without having to actually measure it with the appropriate sensors that you would normally use. And Gaussian regression and with our classifiers gives us a very accurate means of estimating the soil in terms of what we would want to do for adaptively digging. And that is my presentation. So if there are any questions.
Any questions from the audience? I'll ask one. Okay. Adam, great talk. So when you're doing the classifier, you're assuming, does the classifier get thrown off when you have, let's say, if you hit a rock bed or a different kind of granulated rocks, and what are your thoughts on that?
So are you asking, like, if I'm drilling and I hit one of those items that maybe it's not like a smooth trace down through the soil? Mm-hmm. So in the training we did, it would account for it. And I think that's why it's, we have so many data points. And if you look at soil without those impediments, it tends to be, even though it's random, it's fairly predictable in terms of its properties as you transition downward in a small instance. So I think what happens is when we do hit those impediments, it does throw the algorithm off slightly in terms of the ability to be hyper accurate with our results.
Okay. And then one final quick question. Do you actually have to take out the augers after, let's say, a certain amount of time, or?
That's excellent. I'm sorry I didn't mention that. The idea is that we leave it in the ground and the aircraft flies away and the auger just stays there with the sensor in the soil. It's a long-term thing.
Okay.
And in fact, like, the aircraft can just fly to a location and land, or it can just fly. We don't even worry about recovering the aircraft in some sense. It's a disposable system.
All right. Thank you very much, Adam. So I think, thank you. We'll have a quick discussion session. If we can, I think everyone is virtual, so it makes it easy. Great talks by everyone. We had like a wide range of talks in mapping and localization. We went from mapping with human dynamic scenes to roads to under subterranean challenges, as well as some getting dirty with the dirt and getting the wheels dirty, as well as the auger system. So great talk, everyone. Just to keep it to mapping and localization, as a human, when we navigate, we don't really do metric kind of mapping, right? We more do semantic based. We say go from one room to another. In the 3 talks that earlier we saw, a lot of emphasis was mentioned on like not having metric way of mapping, of trying to rather, instead of getting using the feature extract, instead of extracting features, try to just use more semantic based mapping and localization. So as the authors, what are your thoughts on general semantic-based versus data association and feature-based mapping. And what do you think? How do you think the field is evolving in that terms? Anyone can start.
Maybe I can say one word regarding our work. For us, in general, it was important to have the metric component because the SAT was requiring to report the location of artifacts in this regard. And also, I see opportunities potentially for state estimation in combination with planning, where you can express your goal, or, with respect to some semantic class, and you may want to close the loop around that directly, avoiding maybe to accurately estimate the state in terms of metric and just do everything in a relative sense. But yeah, for subterranean domains, semantics may be challenging because the environments tends to be rather repetitive. At least that's what we had seen at the beginning, but maybe some may disagree. Yeah.
So anyone else, Xinjiang or Sheng?
I think the most SLAM approach will mainly focus on the spatial information mapping, right? I think the spatial information mapping have been outperformed the human level because you got a 3D LiDAR and you walk around the campus and you can fully reconstruct the spatial information of the campus. But for the human, people cannot reconstruct the detail, right? But you will extract the semantics information, like there have some corridor and there have some landmark, right? So we are mainly focused on the human-like navigation, not the robot-like navigation. So we are focused on some other semantics information like pedestrians flow or crowd flow, or we also focus on some other semantics information understanding. Yeah.
Yep, thank you. Anyone else? I know Adam and Chris, you're slightly away from mapping and localization, but feel free to jump in. So just to add, if you have time, I think another question was, we saw both visual as well as laser-based SLAM work in this talks. So I think the first two were monocular, we had some, and then as well as second and third were more about laser-based. So any thoughts on those going forward? I guess maybe I'll ask John on it.
Yeah, and we've recently done some more evaluation of some visual SLAM-based techniques, and I'd like to point out that we've noticed that there's a lot of challenges in getting this to work on actual robot systems. For example, one of the big problems is to perform loop closure, you not only need to get to a similar point of view, you also need to have the same, the same direction of view. And so is that as likely to happen in an autonomous robot run unless you're explicitly, controlling the robot in order to make those observations? No. So we probably will need to include closing the loop in the autonomy system itself, to make the visual SLAM more practical. And I think we talked a little bit about the difficulty of running visual SLAM in more challenging subterranean environments due to lighting, and there's quite a few issues there.
All right, thank you. I think we are running a little late with the time. I think thank you all the authors for their time and presenting.